So we're continuing our discussion about radioactive atoms. And now we're going to look at an important concept called half-life, which you might have heard about before. So to do it, we'll look at an example of a radioactive element that we haven't seen before. This one is iodine, which is number 53 on the periodic table. So it has 53 protons. And this particular isotope of iodine is called iodine 131. So it has a mass number, we know, of 131. And let's draw the atomic symbol, number 53 and 131. So here's what iodine looks like. It's a non-metal, but it's still a little bit shiny. It looks a bit like carbon, the graphite form of carbon. So if we have some iodine 131 and we look at all of those, or if we look at 100 of those atoms, there's actually trillions and trillions of atoms, but if we just look at 100 of them, so we've got our iodine 131. Here are the 100 atoms in our little diagram. And remember that a nucleus decaying, when it's radioactive, the amount of time that it takes is completely random. So one nucleus might decay straight away as soon as we pick up, or as soon as that element is made. But then another nucleus of iodine, it might take years and years to decay. And the amount of time that it takes it's hard to measure because they're all taking a different amount of time. So the way we actually measure it for a whole element is we say, how long does it take for just half of those atoms to decay? And that's the half-life. So the half-life is the time taken for half the atoms in a sample to decay. Another way of picturing radioactive decay is like a glass of water evaporating. So when we put out a glass of water, all those water atoms in the glass, we can't predict exactly which one will evaporate when, but we know that over time, those atoms will turn into a gas. So eventually, that cup will be half full. So each individual atom we don't really care about. We're just looking at overall how long does it take for half of them. So here's our 100 atoms. And for iodine, we can see in the next picture, half of them have become radioactive and they've decayed. Well, they were always radioactive, but they've decayed and turned into their non-radioactive form. So we call this time here one half-life. And then if we keep waiting and keep waiting, then half of those will eventually decay. So there's only a quarter of the atoms left radioactive. All the other ones are stable now. So that time we'd have to wait 2 half-lives for that time. So a half-life is really just a measurement of time. And then finally, half of those would eventually decay, and we'd have to wait 3 half-lives for that. So the half-life of different radioactive isotopes can differ a lot. We've seen carbon-14 before, and its half-life is about 5,000 years. Whereas something like uranium and uranium-238, its half-life is 700 million years. And other isotopes, they have a half-life of just a few minutes, or some even a few seconds. And these ones in nature, they will need to be produced by something like rays coming from the sun, because they'll break down and decay within a few seconds. So why is the half-life important? Well, here are two main reasons. The first is when we use radioactive materials for things, we produce radioactive waste. Radioactive waste. So often, particularly when we use uranium to make power in nuclear plants, we have a lot of radioactive waste, and that uranium is still radioactive. And remember, uranium's half-life is 700 million years. So we are producing barrels and barrels of uranium waste, and that's not going to break down for billions of years. So we need to be really careful where we dispose of it. Sometimes we can bury it above the ground if it's in a safe area, but other times we need to dig huge tunnels and mines and keep it underground. And that's still a problem that future generations will have to deal with, because we can never dig up these areas and they'll never be safe for billions of years. So it's a big issue. And it's even more of an issue when there's a malfunction at a nuclear power plant. So you've probably heard of Chernobyl before. And at Chernobyl there was a big accident, and the reactor was poorly designed and the reactor exploded. And there's still to this day radioactive uranium in the reactor, and it's still releasing radiation, and it still will. So accidents can create areas that are just uninhabitable, so people can't live near that reactor pretty much for millions of years. Because radiation has infected the whole area around that town, and they had to evacuate the town, and nobody lives there to this day. We have actually built a giant structure that goes over the top of the old structure, so we're starting to make it a bit safer, but that uranium will still be there, and the area around it too. So lastly, we can look at a graph version of half-life 2, which can help us to picture what's happening. So on our graph, we can look at the percentage of the isotope that's radioactive still remaining. We've got 100% at the start, and then after one half-life, there's only 50% remaining. So that time there is one half-life. Then when half of that has decayed, we're down to 25% remaining. That's 2 half-lives. Half of that is 3 half-lives, and so on. So radioactive decay, this type of graph, when you start doing graphing in maths, this is an exponential graph. And we call it exponential decay because it's going down. So the half-life is the time it takes for half the radioactive atoms to decay and become stable.